Here is a problem in a textbook. Take a look. So, how do we solve this problem? Well, first, we have to figure out some symbols. I'm going to call my subscript D for David. This will be David's position as a function of time. Likewise, we're going to have Tina. Tina will be a subscript T, and her position will be a function of time. Now, both these equations are given by a kinematic equation. So first I'm going to assume that the acceleration is constant for both. For each of them is constant. That allows me to justify using the kinematic equation. Well, this can help my strategy if I first draw a diagram, a picture, or a graph, but something kind of graphical. You can think of it as a map to tell us where we're going. So here I'm going to choose to draw x as a function of time, and I'm going to draw both Tina and David's position on this graph. Now David's easy. David is just following a constant velocity. And remember, position as a function of time, if we want to get velocity, it's just the slope. So if the slope is constant, then the velocity is constant. So this is going to be David. Now, I also get to choose when time t equals 0 is, and where x equals 0 is. Now in this case, what makes sense is to call time t equals 0 when David passes Tina. So that's when David first meets his doom. He just doesn't know it yet. So at t equals 0 they meet, and that's also x equals 0. Tina starts accelerating almost instantaneously because, again, Tina is a baller. She starts off slow. After 1 second she's only going 2 meters per second, but she picks up more and more speed, and under constant acceleration the position as a function of time looks like a parabola. And what we're trying to do is find out, where do the two meet? And where does David get his comeuppance? So this time is when they meet. And the first question, part A, is asking, how far does Tina drive before passing David? Well, this is how far she drives. So this is x. T is a function of t. This is how far she drives. So we just need to figure that out where they meet. Okay. We use the kinematic equation. David's position is going to be his initial position at t equals 0, which in this case is just 0, but I'm just writing it down for completeness. It's going to be his initial velocity times time, plus, again, just for generality, I'm putting in the acceleration term in case David has some acceleration, which he doesn't. Tina starts off at some initial position, t0, but also some initial velocity, t0. These are going to be 0 here. And also an acceleration. Okay. Now my knowns are that I get to choose my position coordinate. So David starts off at 0, Tina starts off at 0. Tina's velocity also starts off at 0, we know that. Her acceleration is given in the problem at 2.0 meters per second squared. David's initial velocity is 30 meters per second, moving pretty quick. It's like 60, 70 miles an hour. His acceleration is 0. Okay, so do not plug in numbers into your equations unless they are 0. Just follow that rule, okay? In general, follow that rule and you should mostly be okay. So here I can plug in my zeros, in which case I get to cancel out some of these things. That's going to be 0 because my acceleration is 0, or David's acceleration is 0. His initial position is 0. So I'm going to get a nice simple equation. Oops, use my blue. xd, that's a function of time, is given by vd 0 times time. And I'm not plugging in 30 meters a second just yet. Don't do that till the very end. Now likewise, with Tina, her position as a function of time is going to be 0 plus 0, just simply going to be given by an acceleration term. Okay, and now what I want to do is find out where these two have equal values, so that they're the same position. So I just set these things equal to each other, and I could solve for the time. Okay. So Vd0 times time is equal to 1/2 AT t squared. I can divide both sides by time. That's going to subtract 1 from the exponent. So this is equal to 1/2 acceleration of Tina times t. I think that would be a good band name, the acceleration of Tina. Okay, let's solve for t. This is when they meet. So t meet is 2 times David's velocity divided by Tina's acceleration. Now I could plug things in if I want, just as a check-in. David is moving 30 meters per second. Tina is accelerating at 2 meters per second squared. This is 2 times 30 is 60, divided by 2 is 30. What about my units? I can cancel out the units in the same way. 1 second, 1 over seconds cancels out with 1 over the 1 over seconds down here. This is in the denominator when it's in the denominator, so it can be flipped up into the numerator. So this is the right units. Okay, so they meet after 30 seconds. Now we just need to figure out where is Tina. So Tina now, at 30 seconds later, is 1/2 2 meters per second squared times 30 seconds squared. 30 squared, well that's 3 times 10 squared. So 3 squared times 10 squared, that's 9 times 100, 900 seconds squared. 1/2 times 2 is 1, so this is 900. The second squared cancels out with this second squared. 900 meters, that's the right units. That seems about right. So almost a kilometer later is when Tina catches up and really ruins David's day, but he deserves it. What is her speed as she passes him? We didn't answer that question. So her speed now, to figure out speed, we could take the derivative of this equation, or you might just remember it. Tina's speed as a function of time, her velocity as a function of time, is given by her initial velocity, which in this case is 0, times her acceleration times time. This is 0. Her acceleration again is 2.0 meters per second squared, 30 seconds. So 2 times 30 is 60 meters per second. Tina is going very fast when she meets up with David. So that's part B. Part B and part A.